So friends, today we would like to discuss about superposition of linear deformation. So in this topic we shall be learning how to use the principle of superposition to get deformation in the member. So before going for actual topic, let me tell you the basic concept of linear deformation. So in order to understand the linear deformation, the first thing is we should know about the linear strain. So if you look at here, we have a bar of length L having area of cross section A and Young's modulus E. When this bar is subjected to the tensile load P, this bar is going to deform and there will be elongation. So if you see here, when you put this bar under the tensile load of P, there will be elongation in the length of the bar, and delta L is the elongation in the length of the bar. And the linear strain is defined as the ratio of the linear deformation to the original length of the bar. So it is a ratio of, so that is the linear deformation is delta L to the original length of the bar, that is L. So this ratio is called as linear strain. We also know that there is a relationship between linear strain and the stress. So stress is basically load, the load, tensile load P divided by area of cross section. So you can find out the relationship between stress and strain by using Hooke's law. So we have the linear strain epsilon equal to linear stress divided by Young's law. So this particular expression is derived from Hooke's law, because by Hooke's law we know that the linear stress is proportional to linear strain, that is linear stress sigma equals to Young's modulus time linear strain. So this is by using Hooke's law we have got that the linear strain is the ratio of linear stress to the Young's modulus. Now we can substitute the value of linear strain as delta L by L. So you will get delta L by L, which is nothing but the linear strain, is a ratio of linear stress. Linear stress is nothing but load upon area, load divided by area and divided by Young's modulus. So this will be further simplified. So you will get the expression of delta L from here. Delta L is nothing but the linear deformation what we are looking for. So we have got the expression of deformation in the length, which is linear deformation, as load multiplied by length, that is P into L, divided by area of the cross section multiplied by Young's modulus. So we got the expression for deformation in the length as PL by AE. Now this is the case when we have a simple member and which is put under the tensile load P. But if there are various loads acting on the bar at various cross sections, okay, so in that case we are going to use the superposition of linear deformation. So what is the superposition of linear deformation? It is the total deformation is the algebraic sum of all deformations produced across various cross section of a member. Now let me explain you what is the meaning of superposition of linear deformation. Suppose we have a member which has various cross sections. So if you look at this example, we have a member, there are different forces acting across the various sections. So there may be some different force acting across this section, let's say P1 here, you may get some force acting over here, P2, you may even get here another force, and here you may be getting, let's say, P5. So you can see that there are various forces acting across the different cross section. So if I call this as a first, this is a second, this is third, and this is fourth. So each of these are experiencing different forces and they will be having some different deformation. So each section of this member is going to have different deformation. The first section of the member is having deformation delta L1. The second section of the member has delta L2 deformation. Similarly, we have delta L3 and delta L4. So each sections of this overall member is going to get different deformation. So now if we have to find out the overall deformation in the member, it is going to be the algebraic sum of individual deformations. Now whenever we do the algebraic summation of individual deformation, we have to be very careful that if there is an elongation in the member, that is going to be called as positive deformation. If there is a compression in a member, it is going to be called as negative deformation. So tensile deformation or elongation would be taken as positive and the compression would be taken as negative. So there is a sign convention we have to follow, and the sign convention is something like this. That is, for tensile we take it as positive delta L, and for compressive we take as negative delta L. So overall deformation is going to be algebraic sum of individual deformation. So it is plus minus delta L1 plus minus delta L2 plus minus so on. So this plus minus would depend upon the nature of the deformation. It is compressive or tensile. So by using this particular method we can find out the overall deformation in the member. So we will do one example based on this in order to find the overall deformation in the member by using superposition of linear deformation. So let's see one example here. Now we have a problem here, you can see. So let me read the question for you. So a bar having Young's modulus E equal to 1.05 in 10 raised to 5 megapascal and the cross-sectional area 1000 mm square is subjected to the axial forces as shown in the figure. Find the total elongation of the bar. So if you see in this particular example, we have a bar ABCD, so which is having various forces acting across the sections. So we have, this is the one section we have, this is the second section we have, and this is the third section we have. So we have to find out the overall deformation in this member due to application of these forces. So what we shall do is, we shall take each section, section 1, section 2 and section 3 individually, and we'll see the nature of forces acting on each sections, section AB, section BC, section CD, and on the basis of the nature of forces we will calculate the deformation in the each section, that is delta L1, delta L2 and delta L3, and then by using the principle of superposition we will find out the overall deformation in the member ABCD. So let's do it. So we have drawn the entire member ABCD over here. So we have drawn the member A, B, C, D over here. So length of this particular member is 600 mm. So we'll try to keep same unit. So it is, the length over here is 1 meter, so we'll call it as 1000 mm, and this is 1.2 meters, so it is 1200 mm. So we shall keep same units throughout. Now let me take this first section AB. So if you look at section AB over here, the left side of the section is having 50 kilonewton load. So obviously the right side of section AB should also carry the same load, because to balance 50 kilonewton tensile there has to be a 50 kilonewton tensile. So we will always deal first with the end sections, that is AB and CD separately, and then we will try to understand about BC. So we will take first section AB, and since a tensile load of 50 kilonewton is acting on section AB, so that we will show here. So this is the section AB, so we have taken section AB first. Now since 50 kilonewton is acting over here, the same amount of load must act towards right. So here also you should be getting 50 kilonewton. So we should always take first the end sections of the member. So I have taken this. So member 1 has load 50 kilonewton, both are tensile. So it will be, I'll write it down, the load P1 which is acting on the section is positive, tensile is positive, 50 kilonewton. Now the next one is this section 1 we have taken, and its length is 600 mm. So I'll write down here L1 as 600 mm, and third, the area of cross section is same throughout. You can see here, so it is given as 1000 mm square. So A1 is 1000 mm. So I have listed down all the available parameters. Fine. Now I'll take the next ending section, which is CD. So if you see the next ending section, section CD, so it is getting 10 kilonewton compressive load here. This is my third section, I can say. So this was second section, this was third section, so I am taking third section, that is section CD. So it is getting a compressive load of 10 kilonewton. So naturally, in order to balance 10 kilonewton, from this side also 10 kilonewton load must be acting. So I'll write down here load of 10 kilonewton, that is compressive. So naturally the second ending section has a compressive load of 10 kilonewton. So I'll write down P3 as minus, because it is compressive, 10 kilonewton. Length is given as 1200 mm. So L3 is going to be 1200 mm, and area is same for third section also. So A3 is again 1000 mm square. Now the remaining section is the section 2, which is BC. So I'll draw it here, and we'll try to understand what loads are going to act on the section BC. So BC is here, this was CD. Fine. Now if you look at here, so let me take this left side of the section BC. So on this we have a 80 kilonewton compressive and 50 kilonewton tensile, because this 50 kilonewton load will also have effect on section BC. It is going to have effect on this area also. So this section is going to experience the load of 80 kilonewton compressive as well as the load of 50 kilonewton tensile. Both are going to be acting on this section. So 80 is compressive and 50 is tensile, so net effect would be 30 compressive. So you will be getting net effect as 30 kilonewton compressive, because 80 is compressive and 50 is tensile. Here also if you see this section, so it is having 20 kilonewton compressive and 10 kilonewton also is going to have effect on this. So 10 and 20 is going to be 30, so you are going to get 30 compressive. So this is very important to understand. So you will have 30 kilonewton compressive. Okay, so we got 30 kilonewton load compressive here as well as 30 kilonewton compressive here. Now there is a cross check over here. If you get both the values same, then only your method is correct, otherwise there is some problem. So always you should check for it that both the values should come correct, same. If both the values are same, then your method is correct. Now for section 2 we have got the forces, that is P2 as 30 kilonewton, which is minus because it is compressive. The length is given as 1000 mm, L2 is 1000 mm, while area is same for that also, E2 is 1000 mm square. So this way we are able to get the required parameters. Okay, now we shall find out the elongation in the each member. So we will try to find out delta L in the first member, that is delta L1, delta L2, delta L3. So if you look at what we have done in the previous slide, so elongation in each member is PL upon AE. Okay, therefore total elongation delta L is going to be, that is delta L is going to be, now if you look at L1, delta L1 is tensile, so it is plus delta L1. Delta L2 is compressive, so it is minus delta L2, and delta L3 is also compressive, so therefore it is also minus delta L3. Please remember, this is tensile, this is compressive, this is compressive. So we have taken signs accordingly. So therefore you will get delta L is going to be, we know that delta L is nothing but PL upon AE, so it is going to be plus P1 L1 upon A1 E1 minus P2 L2 A2 E2 minus P3 L3 A3 E3. If you look at here, this value of AE is same for all members, area is same and Young's modulus is same, so I can take AE as common here, so you will be getting 1 over AE, which is common in all terms. So P1 L1 P2 L2 P3 L3. So if you put the values and you solve it, overall elongation you will be getting as 1 over area is 1000, E is 1.05, you can see here in 10 raised to 5. Please remember the MPa unit, they have given MPa. So 1 MPa is nothing but 1 newtons per mm square. So we are following newtons per mm square. So load we have taken in the newtons, while area we have taken in the mm square. So we are following this same unit. You are getting times P1 is how much? 50, and it is in kilonewton. So always 10 raised to 3 would come, because we are following newtons per mm square, times L1 is 600 minus P2 is 30 kilonewton, so 30 into 10 raised to 3 times length L2 is 100 mm, 1000 mm, and then minus you will have P3 is nothing but 10 kilonewton, so it is 10 into 10 raised to 3 times L3 is 1200 mm. So if you solve this value, you will get the overall deformation as minus 0.1142 mm. So the total deformation delta L is 0.1142 mm, and that is a reduction in the length. Similarly, you can find out the deformation in the members by using superposition principle. We shall see some more examples. Thank you very much.